morning, everyone. My name is Ken Grob. I'm with Elma Electronic, Inc., and today I'd like to talk to you about technology transition in VPX, and specifically how boxes are becoming boards. And as I was thinking about this, I realized that's not too good for Elma since we make boxes, but that may be why we bought an equipment rack company. So anyway, technology drivers affecting VPX. What's kind of happening out there? Use of high speed, and that's supposed to be Ethernet. I got carried away with internet. Ethernet between modules. We're seeing, we've been looking at sort of 1000BX or gigabit in the architectures for years and wondering when we were really going to see high speed 10 gig come into the architectures. And this is actually occurring. We're starting to have our customers push us on this, where we're not seeing 10 gig Ethernet just being used for the egress out of the box or link aggregation within the boxes. We're seeing it being used in the data plane and also in the control plane. With that, with fabric devices that are being used in Ethernet switches, we're starting to see PTP be an integral function of the hardware. So Precision Time Protocol, or IEEE 1588, is starting to come into the switch solutions. With respect to interconnect within the system, we're also seeing PCIe Gen 3 being used either on the data plane or the expansion plane. And something new, which has been done in ATCA for a while, which is radio clocks. We're seeing the need for new clock schemes to synchronize things in the system architecture, and specifically, as DRS spoke today about radio systems. When building radio systems, there's a great need for this. Then looking at single board computers, as we look at new developments from Intel, we've been at Gen 4 or Haswell for a bit, and now moving on to Skylake and Broadwell DE, we're starting to see single board computers that are capable of 10 gig KR native right out of the chip, which is quite interesting. And also chips that actually can have up to 16 cores, so you can have a server on board solution. The last point is changes in FPGAs. In FPGAs, we're seeing system-on-chip solutions where the processors are being embedded in the FPGAs, which gives you quite a big capability at the chip level. So this increased chip density and system-on-chip solution allows the board functionality to increase, and this allows box-level solutions to actually be able to be collapsed and implemented at the board level, which is great for swap-C. So a few examples of where we're seeing maybe a box-level solution reduced to a board-level solution would be with servers with the new Xeon D multi-core processor, quite high-density Ethernet switches on 3U VPX boards that are capable of 10 and 40 gig, and an FPGA system on chip. So I have a few examples. This first board on the left is actually a Xeon D processor. It's 32 gigabyte DDR4. First comes out in 8 cores or 16 threads, and then it'll go to 16 core, 32 thread. And it has native 10 gig capability on it, which I found interesting. When you turn on the activity monitor, you actually see 16 threads running. So you're looking at 16 computers within one chip. That kind of blows your mind when you look at it, because you're used to seeing that being 1 or 2 bars. Now it's 16. And you're like, wow, that's pretty cool. So if you're thinking about connecting that, then you have 2 big fire hoses coming out of that computer, and you need a fabric to interconnect it. So now there are switches, and these are coming out from a number of manufacturers. This one's from Interface Concept. We have switches like this we've seen from Contron. I think Curtiss-Wright's working on new switches like this, where we're looking at 10 gigabit capability in the fabric and also 40 gigabit capability in the fabric. So we'll have very wide pipes that can interconnect the boards, passing high amounts of data between them. And also fiber optics, and I saw Reflex Photonics will be here today talking about great stuff that's happening in fiber to get things in and out of the board. That's a QSFP Plus cage on the front of this one, showing how fiber can take 10 gig or 40 gig out the front of the card. So the system on chip and FPGAs. This is kind of a mind blower. You look at what is coming in UltraScale and UltraScale Plus from Xilinx. This chip actually has multiple ARM processors in it. It has a GPU in it. It has a secondary ARM core, so before you even get out of the left-hand corner, you're looking at multiple processors. They're 64-bit, very high performance. And then in the middle of this, you have a graphics subsystem, and then you have the entire FPGA logic pool that's inside the device. This device will be able to use very high-speed interconnect at 100 gig as the transceivers become quite high performance. So when you look at a device like this, you can put one of these on a VPX card. You have an entire system within an FPGA that's quite capable. So proper billing here. Altera also developing similar things with the Urea 10. Same story, integrated processor, very high speed transceivers in the device. And this one not quite getting to 100 gig, I don't believe yet, at 28 gig on the transceivers. But entire systems on chips that then can become systems on modules. So if you look at what you can do with that from Altera's point of view, this is a Cyclone 5 that's an FPGA and a processor within the FPGA, and that can be put on a module that can be reused on a board. This can save you lots of time in design because all the high-speed stuff is done within the module, and then you can use a high-speed connector and plug that onto something like a VPX card or whatever your base board is, a motherboard. So, excuse me. So looking at an initiative from the US Army called Hardware Convergence, what are the technology drivers that we're seeing coming from that? And the thing on the right is basically a backplane profile diagram. And I know you can't quite see that. I have a bigger picture of it coming up next. But what it discusses is the need for some of the technologies that we talked about earlier. And specifically, one of those is radio clocks. So we don't have one clock or one system clock in the board, which was designed in the VPX specification. We actually have the need for time management reasons to connect with radio clocks from a clock reference card. So if you go down and look at those technologies that are being driven by an architecture like this, high-speed interconnect, this is kind of interesting. All of the IOs in this backplane architecture are high-speed. Everything has to be 10.3125. So that makes the backplane quite a challenge, but it lets you support 10 and 40 gig Ethernet and also lets you support PCIe Gen 3. When you look at systems that are complex, where boxes are being folded into boards, it challenges what you do with I/O. And two areas where I/O needs to be looked at is in transitioning RF and fiber optic. So new types of connectors are necessary to support that. Now, the radio clock scheme increases the speed of the clock. 10 megahertz used to be a common number. Now it's going to move to 100. And the other thing we see with all this going onto a board is power density and the need to cool 3U VPX cards now pushing 45 to 50 watts. So if we look at a bigger version of this, we actually have multiple domains within the architecture, multiple processors. There's 4 of them in here. And you see in the red area the radio clocks. Then you see data planes and control planes capable of 10 and 40 gig. And as you go down towards the bottom, you notice that there are these new gray blocks, which are based on Vita 67.3 connectors, which the gentleman from DRS had pointed out prior, to take both RF and fiber optic I/O out of the box. So impacts to the backplane. With everything being 10.3, I think it's 125, you really want to buy your SI guy flowers or candy or something like that to keep him happy, because everything in the backplane and in the board needs to be SI modeled. It's very, very difficult. The PCB material is changing. FR4 no longer cuts it. We need to move on to new materials like Megtron 6. And actually the weave in the PCB makes a difference. So fiber weave, it gets that bad, where you're trying to keep signal skew balanced in the backplane. You actually have to be concerned about that. So as we put a lot of IOs onto the card and the chips get bigger, it's increasing the densities of the backplane. Theoretical maximum for the backplane is 40 layers. And we're running in like the 12 to 18 layer range. Now we're looking at 24 to 32 layers. And then lastly, we use in VPX a multi-gig connector. And the multi-gig connector is starting to become a challenge because we're hitting the limit at 10 gig, and we're also seeing some issues with isolation. So the good news is that backplanes can be built using new materials and good SI modeling techniques, et cetera, to support the rates that are required. So looking at VPX, great thing about VPX was it was designed to change. And now we're all using OpenVPX or Vita 65, but it allows new profiles and new technologies to be introduced and ratified and brought into the specification, which is happening with the architecture that we were looking at earlier. Other new things follow on to the FMC specification. As those FPGAs get bigger and faster, we need better connectors and a different spec there, so that's being worked on. Conversion, I think it's, what is that number, Jerry? Is it 57.4? 4. Cooling specs, as we make these systems, we see power being an issue, so we have to get more creative in trying to get the heat out of the boxes. Channel spec, this is the spec that defines the high-speed channel definitions in our world. So for high-speed interoperability for all of us, this is important because to our customers, the specification of the products aren't very good unless they all work and play nicely with each other. And then lastly, connector specifications where we saw Vita 66.4, 66.1, and 66.2. Now moving towards a new definition, 67.3, which allows you to make connectors that fit your need and then ultimately contribute them back to the specification. So if we look at radio clocks, there's a profile that's in Vita that defines the radio clock profile, which allows you to build a clock distribution card and distribute these radio clocks and also provide 1 PPS signal for things like GPS. For the switches, as the switch topologies change, we need to define the slot profiles for the switches, and we also need to define the module descriptions. And then when you look at the backplane itself, the backplane starts to change the way that it used to look. Now you see the connector profiles towards the bottom with Vita 67.3 connectors, and the Vita 67.1 and .2 connectors that are in existence actually can become compatible with 67.3, and that 67.3 can become intermatable with a 67.1 or a 67.2. So I think Mike Monroe is going to talk about some more of this tomorrow, but this is a little bit of an overview of what's happening there. So if we look at the VPX Road Map, where's everything going? We flip the page in the book. Greater use of fiber optic going forward. We actually can see copper running out of gas. We're at the place where in the next generation of PCIe Gen 4, we will no longer be able to use copper for the interconnect. 100 gigabit Ethernet requires 25 gig per lane, so this requires fiber optic to get it off the board, but also to go between boards. We won't have a connector that's good enough to support that in copper going forward. So what it also drives is the need for a next generation multi-gig connector, which we understand from our friends at TE Connectivity that this is happening. When you look at PCIe Gen 4, it'll double the bandwidth from 8 gigatransfers per second to 16 per lane. That's like, I think, a lane bandwidth of around 2 gigabytes per second. And this will be the last stop for copper within VPX. To get there, we'll need a new connector, and that's from what we understand in the roadmap. So that's coming. So this is all good news for VPX, showing that VPX will continue and it has legs. So in summary, VPX is evolving to support new architectures. As it was designed to grow. New I/O types are being supported in VPX, allowing high-density fiber to be used. RF I/O is supported for getting RF signals on and off VPX boards. And the new connector that's in the works will provide a path going forward to Gen 4. So we'll be able to go to Gen 4 within the cards. And then high-speed backplanes are able to keep up with this. We can build that to support the bandwidth with the new I/O connectors and the new architectures. So at the end of all this, what we see is VPX systems will provide feature set and a platform for very long life systems life cycles, which the military needs and which gives us a platform that we can grow with. Thank you.